Two separate but frequently conflating issues are essential for alarm: the magnitude of warming and the relation of warming of any magnitude to the projected catastrophe. I mentioned before the business of the prosecutor's fallacy. This basically, in its simple-minded sense, says the near certainty of the fact that if A shoots B, there will be evidence of gunpowder on A's hands, and confusing this with the assertion that if C has evidence of gunpowder on his hands, then C shot B. Everyone, I think, can see the fallacy in that line of argument. With global warming, the line of argument is even sillier, and I've given this before. Generally amounts to something like, if A kicked up some dirt, leaving a dent in the ground into which a rock fell, and B tripped on this rock and bumped into C, who was carrying a carton of eggs, which fell and broke, and then if some of the broken eggs were found, it showed that A had kicked up some dirt. These days, we go even further. We decide that the best way to prevent broken eggs is to ban dirt kicking. Some current problems with the science. There's questionable data. And as we've seen, this is a kind of tricky issue. ClimateGate focused a lot on manipulating data. And I feel this is a complicated ethical issue for several reasons. The small temperature changes are not abnormal. Even claimed changes are consistent with low climate sensitivity. The issue becomes important because the public has been misled to believe that whether it is warming or cooling, no matter how little, is of vital importance. Thus, tilting the record slightly is of little consequence to the science, but of great importance to the public perception. And so the question is, where do you deal with these manipulations? How? More sophisticated data is being analyzed with the aim of supporting rather than testing models. If you look at the IPCC, most of the data is dealing with what they call validation. What you find remarkably absent in climate science is designing tests that can be failed, which is the essence, in some ways, of science. You can see that, when I was on the IPCC, I was also on the National Climate Assessment Program in the US. The emphasis there was always on validating. And can get lots of examples of this. Now, when I speak of measurements, it's important to keep something in mind. I think the picture most people have from school in terms of measurement is a careful laboratory measurement, charge on the electron, the mass of something or other. And this is what people associate in their minds with data. But in the case of climate and all the things we're specifically mentioning here, we're not dealing with simple measurements. We're dealing with huge collections of sometimes dubious measurements that are subject to subjective analysis. When it gets too extreme, as with the GISS example, it would be probably more apt to refer to it as massaging the data. Now, I've often mentioned that sometimes one can use theory in this field to establish that data is wrong, which is something that sounds counterintuitive to people when they think about science. This is a case, it has to do with something called a hotspot. When you run models and you double CO2, if you plot the temperature change as a function of latitude, the horizontal axis, and vertical axis is altitude in pressure levels, you find that the maximum warming occurs around 200 hectopascals So around 12 kilometers above the surface. And it's 2-3 times the warming at the surface. There is ample reason to assume the models are correct. And the reason for that is convection, which dominates the tropics, forces the temperature along something called the moist adiabat. And it will have this characteristic when you warm. So it's simply a statement that the models have the moist adiabat, and convection is operating in these models in the tropics. Needn't even operate totally correctly. On the other hand, when you go to the data, this is again from Hadley Center, UK Hadley Center, you don't get this 2-3 times the warming at 200 millibars that the models show. Indeed, the warming is a little smaller than at the ground. What this is telling you is one or both of these measurements is wrong. If the surface is wrong, then it says that the warming trend given by A has to be moved to B, which should be about 2-3 times smaller. And that would again have some very interesting implications. The question is, what is an error? And the answer at this stage is it's not clear, but given the uncertainties in the analysis, such errors are not out of the question. Now we come to the issue of sensitivity. This is a crucial issue. How much warming do you expect from a doubling of CO2? In truth, it can't be determined from the time series for the data. And the reason for that is to do so would assume you know everything that can cause these changes. If, for instance, you're wrong, you've left out one cause, you see a change and you don't see a change in CO2, if you thought that the only thing that could change it is CO2, you'd get infinite sensitivity, because nothing caused something. This problem infects almost all attempts to infer climate sensitivity from paleoclimate data, meaning data from the ice ages and so on. You also cannot test models by comparing models with models. The models are not basic physics, and it's possible for all of them to be wrong. There's no special virtue to the average of all models, which the IPCC does, without respect to the qualities of any individual model. As I say, these are all central to IPCC reports. These are the authoritative reports endorsed by the national academies and numerous professional societies. Now, here is an example of the current state of science. It's again going back a year or two. It was a letter to the Financial Times by the then presidents of the Royal Society and the National Academy, Martin Rees and Ralph Cicero. Now, of course, you can't read what I have here. I'm going to focus on 3 sentences. The first one is the following. However, as your editorial acknowledges, neither recent controversies nor the recent cold weather, I'm talking about ClimateGate, negate the consensus among scientists. Something unprecedented is now happening. The concentration of carbon dioxide in the atmosphere is rising, and climate change is occurring, both due to human actions. Now, it's an interesting statement. It goes well beyond the IPCC. This is a good example of where people say things and attribute it to the IPCC, even though they've gone way beyond it. So, for instance, the IPCC statement that claimed that only more than half the temperature change over the preceding period could be attributed to man's emissions, with aerosols included to cancel much of the excess warming from the models. Instead, they're saying all. The assumptions underlying the IPCC claim have been shown to be false. Namely, the assumption has to be that all sources of change in temperature are known. But in fact, they shortly thereafter acknowledged that they had left out phenomena like Pacific decadal oscillation, Atlantic multi-decadal oscillation, and so that invalidated their whole methodology. Of course, you can take a sentence like this and parse it. Perhaps they meant there was increasing CO2 demand and there was warming due to this, though it might only be a small part of the already small observed warming. If that's all they meant, the statement is trivial, suggests no basis for alarm. But I don't think there's any doubt in my mind that this is not what they intended the reader to infer. Now, then we come to a second sentence in this letter to the Financial Times. Uncertainties in the future rate of this rise, stemming largely from feedback effects on water vapor and clouds, are topics of current research. Now that's just thrown in, it's in the middle of a paragraph. Who would guess from this throwaway comment that feedbacks are the critical issue? Without strong positive feedbacks, there would be no cause for alarm and no need for action. What Rees and Cicerone are actually saying is that we don't know if there is a problem. Now, then we come to their third statement. Our academies will provide the scientific backdrop for the political and business leaders who must create effective policies to steer the world toward a low-carbon economy. That's fascinating. They've just admitted we don't know if there's a problem, and yet they're saying that regardless of the evidence, the answer is predetermined. If the government wants carbon control, that is the answer that the academies will provide. Nothing could better epitomize the notion of science in the service of politics, something that unfortunately has characterized climate science. So where do we go from here? And part of this is a time issue as well. Given that this has become a quasi-religious issue, it's hard to tell. My personal hope, of course, is that we'll return to normative science, try to understand how the climate actually behaves. Our present approach of dealing with the climate as a single number governed by a single variable, global mean temperature anomaly in CO2, is clearly naive. It is certainly limiting real understanding. So is the replacement of theory by model simulation. Now, that doesn't mean that this has completely dominated the subject. There has been a little progress. I actually think, though, the nature of the issue and its public exposure have inhibited rather than encouraged science. There are things we have found. Looking at the sensitivity independent of models by specifically measuring feedbacks supports the fact that nature is giving us a modest negative feedback instead of a strong positive feedback. There are some cute problems that have been worked on. One is something called the early faint sun. Now, I should ask you, some of you might know the answer to this. When one doubles CO2, what percentage change is one making in the energy budget? It's 2%. Okay? One is attributing all sorts of potential catastrophes to a 2% change in the budget. Now, what's nice about the early faint sun is the nature of stars fed by fusion is that they brighten with time. And if one goes back in the Earth's history 2.5 billion years, the solar constant should have been not 2% less, but 20-30% less. And the geological evidence from that period is the planet wasn't frozen. In fact, its climate was, in many ways, about what it is today, maybe even warmer. Question is, how is this possible? I mean, if 2% is going to cause a disaster, 20-30% didn't seem to do anything. For 20 years now, this paradox was first introduced by Carl Sagan. And since the 70s, it's close to 40 years, 80s, people have been looking at a greenhouse solution to it. And so Sagan originally suggested ammonia. It didn't work, has short lifetime. Then CO2 was brought in, and it turned out you would need over 2 bars. That is, say, thousands of times more than at present. And there's geological evidence against that. And then people looked at methane for some years and concluded that if you used the proper spectrum, it didn't work. What we showed recently was that it's pretty easy to resolve the paradox with clouds, as long as the feedback is negative. If the feedback is positive, there's no way of possibly resolving the paradox. So it's a kind of peripheral way. Now, I have a whole bunch of slides, on the science more explicitly. This is the famous one from Bohr, showing the upper curve CO2 and the bottom one temperature. And, the obvious pictures, I think, have been pointed out, that he confuses correlation with causality. Which is a major no-no in science. But moreover, even these curves are good enough to show that temperature preceded CO2 by hundreds of years during glaciation. Since then, it also shows, if you look at these points here, that at least according to this data, previous interglacials were warmer than the present. In addition, there have been some wonderful papers in the last few years by independent groups showing that these cycles of glaciation are in fact, as had been originally suggested by Milankovitch in the 30s, beautifully accounted for by orbital variations. But in some ways, the biggest problem is, again, this single number business. Just looking at a global mean value temperature and CO2. And the reason that's a problem was revealed by some people at Scripps a couple of years ago in using high-resolution descriptions of the last glacial maximum and its ending. Different regions respond in different times. So the South Pacific begins warming here. The equator doesn't begin warming until several thousand years later. The CO2 seems to follow the equator. But it certainly was not the reason for the initial warming. This doesn't tell you what exactly is happening, but it certainly says it is not a simple one-one story. You have the example of the Arctic sea ice disappearing, and that's itself a funny issue. It has a kind of interesting logical flaw. Every year, the Arctic is almost completely covered with ice in the winter. Every year, about 70% of that ice disappears in the summer. Now, If you then say some years it's 25%, some years it's 35%, 10 is now 30-40% of the 30. And so it sounds big. If you take the same thing of the winter coverage, it sounds small. So people are hearing, large percentage changes in summer ice cover in the Arctic. These are the detailed pictures. I won't go through it. There are also similar exaggerations on the other side. We hear that Antarctic ice is at record high levels. This is the graph for that. It's a hyperbolic way of speaking of it. It's increased a bit. Then you look at the temperature in polar regions, and the Danes have been doing this for decades. And you see something kind of interesting, which is focusing on what may be at issue. Summer temperatures in the Arctic have not changed in decades. In winter, you see these huge fluctuations. They can be 20, 30 degrees. And they're kind of random. Pick another set of years, just decadal. The summer picture doesn't seem to have changed. And all this is telling you is there's a lot of physics going on that are completely lost when you take annual means. In the present case, what it's saying is, in the summer, in the Arctic, when you have sunlight, the temperatures seem to be determined largely by local radiative balance. Doesn't seem to be changing. During the winter night, temperatures would be much colder than they are at present, but for the transport of heat. And the transport of heat is by these storms that penetrate. And the temperature changes from one year to the other have to involve understanding why these storms erratically penetrate the Arctic. CO2 doesn't seem to be a major player. Just for the record, summer ice depends mostly on how much ice is blown out of the Arctic basin. And this used to be textbook information. Now, to be sure, while nothing dramatic seems to actually be going on, the anecdotal information can be much more dramatic. And people like this quote, the Arctic Ocean is warming up, icebergs are growing scarcer. In some places, the seals are finding the water too hot. Reports all point to a radical change in climate conditions and hitherto unheard of temperatures in the Arctic zone. Expeditions report that scarcely any ice has been met with as far north as 81 degrees 29 minutes. Great masses of ice have been replaced by moraines of earth and stones, while at many points well-known glaciers have entirely disappeared. The punchline always is, this is 1922. House effect. And the real nature of this effect is not that hard to understand, but it is not the simple blanket. It is not gases reflecting heat back to the surface. I'll give you also a simplified picture, but it's, I think, accurate. You first have to recognize the nature of what is called the troposphere. It's roughly the first 10 to 15 kilometers of the atmosphere. This is a turbulently mixed fluid. In the tropics, you have cumulonimbus towers. In mid-latitude, you have the cyclonic storms, anticyclones, cyclonic storms, mixing temperature. The way to view it is something that is constantly being stirred, and it's a slab. Because of the nature of the stirring, the temperature decreases with height. We saw this with the moist adiabatic lapse rate. Approximately 6.5 degrees per kilometer, but that isn't too important for this case. This is a picture of the mixing. It has some curious features. The heat from the tropics surface is carried to the tropopause, the top of the troposphere at the pole. But let's not spend too much time. Just let's realize it should be considered a slab. There are gases within the atmosphere that have significant absorption and emission in the infrared. These are the greenhouse gases. And they radiate to space with a flux characteristic of the temperature at about what is called 1 optical depth into the atmosphere. So, you know, the emission temperature of the Earth is about 255 degrees Kelvin. That's about 33 colder than the surface. That's because the temperature is decreasing with altitude. Now, when you add greenhouse gases to the system, that emission level is raised. You don't have to go down as far to reach the same optical depth. And because of the mixing, the temperature is decreasing with height. And so you're emitting from a colder level, and you're emitting less. Because you're emitting less than you used to while the sunlight is still coming in, you no longer have a balance. To reestablish balance with space, the whole troposphere as a slab has to warm. That's essentially greenhouse warming. You can calculate this effect, and it's trivial to show it, give rise to about 1 degree of warming for a doubling of CO2. Now, where do feedbacks come into it? Well, the idea here is, and this is the picture that just summarizes what I just said, you start out with a balance between incoming solar radiation, net minus cloud reflection, outgoing heat. You now add some greenhouse, and so you cut back the outgoing radiation. The temperature begins warming, and the idea in the feedback is the warming causes changes in things like water vapor and clouds, and if it's a positive feedback, it shrinks this further. So the whole system has to warm more than it would just from the CO2. One can in fact measure the radiation associated with changes in temperature. There are problems, there are difficulties with it, and you can finally estimate the feedback factor, and the response of a system, and this is engineering, delta T will be the response of the system in the absence of feedbacks over 1 minus something called a feedback factor. So if you have a positive feedback, this is subtracting from 1 and making this bigger. If you have a negative feedback, it's cutting this down. Now, the zero feedback response is about 1 degree. Okay, so what we did a couple of years ago is just look at satellite data, see events of warming and cooling. They're always a couple of month events, a few tenths of a degree each way, and see how the radiation responds to it. The answer one got from this is that the observations always pointed to negative feedbacks. Not huge, but between minus point, on the total, about minus 0.5. The reason you use lags, and that's important, is ideally you'd like to think the changes in radiation were all feedbacks. And for the long wave, they are, this is how the flux changes with lag, and it's centered a little bit beyond zero lag. That's important because that's telling you cause and effect. If a flux precedes the temperature, it can't be a feedback. Only if it responds to the temperature with a lag would it be a feedback. And for the long wave, it's unambiguous, but for the short wave, you have this S-shaped curve where it changes sign. And what this is saying is you have changes in shortwave radiation that are unrelated to feedbacks, that are causing changes in temperature, and you have others that are predominantly responding. And separating the two is not easy. At any rate, you do the same thing for the models, and you end up with positive feedbacks. And you have the model data because in the IPCC model into comparison, the models produce this for each of their runs. And they have runs where they're forced by observed surface temperature. So essentially, it's saying that while all the models are characterized by positive feedbacks, the satellite data suggests the opposite. And this is not a technical matter. Without positive feedbacks, doubling CO2 doesn't do much. It's only with positive feedbacks that you get the alarm. Positive feedbacks are, from an engineering perspective, implausible. And we'll see why they're especially implausible here. Anyway, when you get these feedback factors and you calculate the sensitivity for the models, you run into a very peculiar thing, at least it seems peculiar. When you calculate the sensitivity according to the feedback factors, the correspondence to the IPCC sensitivities is not that great. On the other hand, if you consider the uncertainties in these feedback factors, you always include the IPCC value. Now, when you do the same thing with the observations, looking at it at different confidence levels, you get very little variation, even for the uncertainty in the feedback factor. The reason for that is this equation, which blows up when F is positive, and then slowly turns horizontal when F is negative. Okay. And this is the picture of that graph. This is the 1 over 1 minus F. And what you have here in the purple, for positive feedbacks, small variations in the feedback factor make a huge difference in the response. Whereas if you have negative feedbacks, you're in the horizontal part of that graph, and big changes in the feedback factor make almost no change in the response. Now, it's the positive feedbacks in the models that leads to this perpetual uncertainty that the IPCC always speaks about. Since 1979, something called the Charney Report, it's always been said that the models give you between 1.5 and 4.5 degrees for a doubling of CO2. The reason for that is the positive feedback in the models, but by no means in nature. This brings up what I think is a pretty good reason for doubting large positive feedbacks. Feedback factor is almost certainly not a constant. It depends on cloud properties. Cloud properties can be altered by aerosols, dust storms, cosmic rays. If you, for instance, have a model that has a feedback factor of 0.8, I personally think, can't prove this, that the odds over 4.5 billion years of that not having gone over 1 are pretty meager. And if that were to have happened, we wouldn't be discussing this. There are other ways to approach sensitivity. One is actually seeing how much evaporation changes at the surface for change in temperature. The reason for that is kind of cute, and it's again a technical one. You know, we mentioned that you have a radiative imbalance when you add greenhouse gases. That's at the top of the atmosphere, seen from space. Actually, the flux imbalance goes through the whole atmosphere, and since you have a fixed lapse rate, it's what's called non-divergent. It's constant with height. But it isn't radiative at all levels. The flux of heat is conductive, it's latent heat, it's convective in general, as well as radiative. So what's totally radiative at the top is almost totally evaporative at the bottom. And since it's non-divergent, the evaporations change with temperature should be an indication of sensitivity. It has been measured. And you have the very interesting result that the models, the evaporation changes about 1 to 3% for a degree change in temperature. And that corresponds to climate sensitivities of 1.5 to 4.5 degrees. And the observed is about 5.7% per degree. And that's back to 0.8 for a doubling. Okay, as I said, there are lots of other things one can discuss, but I think you have some idea of why I don't think there will be much warming due to CO2. Without a lot of warming, it's impossible to tie catastrophes to such warming, and even with significant warming, it would be extremely difficult to make this connection. Beautiful example of that is, I mentioned briefly that what excites variability in storms and so on is something called baroclinic instability. This is an instability which depends on the temperature difference between the tropics and the pole. Big temperature difference, intense storm development, and so on. When you have global warming, you've all been told it should be greater at the poles than at the equator. That reduces the equator to pole temperature difference, right? That should reduce storminess. It should reduce intensity of baroclinic instability. It shouldn't decrease variability. That doesn't sound scary, does it? So you hear the opposite. And it's almost like a bad joke. The assumption is you have no idea what's going on, so whatever they say is fine. In any event, the connections would be difficult. I've long felt the term skeptic is inappropriate. Skepticism, I think, implies doubts about a plausible proposition. Current global warming alarm hardly represents a plausible proposition. 20 years of repetition and escalation of claims does not make it more plausible. Say quite the contrary. The failure to improve the case over 20 years makes the case even less plausible, as does the evidence from ClimateGate and other instances of overt cheating, the latest of which hit the US recently with the theft and forging of documents from the Heartland Institute. In the meantime, I'm not much for making forecasts of tenths of a degree in globally average temperature, but I'm pretty sure I'm on safe grounds in saying that there won't be unprecedented climate catastrophes on the horizon, although in a few thousand years there might be another ice age, There will certainly be climate catastrophes. We've always had droughts, we've always had floods, and that's not going to change. From a societal point of view, you just want to make society as robust as possible. And it's not clear current policies are designed to do that. Thank you.
Ladies and gentlemen, it remains only for me to say the very warmest and most heartfelt thanks to our kind speaker. It's very rare in either house of our Parliament that somebody comes to us and speaks with such an engaging combination of clarity and authority born of profound study and long meditation, and with such an entire absence of political spin. From that, we have a lot to learn. But I think all of us, sir, have learnt a great deal about how the climate hangs together, the various influences, some of which we can model, some of which, frankly, we cannot, and the likelihood or unlikelihood that we're likely to see anything in the way of major warming, and even if there were, major catastrophe arising from that warming. I agree with the gentleman at the back that I wish there were more scientists who, like Dick Lindzen, have been quietly going around, in his case, for the last 30 years and more, giving talks like this to legislators and also to the public, and getting the scientific facts across, and having to endure, as everyone does who dares to question this particular new superstition, the vilification and ad hominem attacks of those who are entirely incapable of arguing with the elegance and authority that you have treated us to here today, Professor. So I ask everyone to give the very warmest thanks to Professor Richard Lindzen.